Okie dokes. Welcome back to CMSC 341, not 341. Okay, so let's talk a bit. So we have to talk. There's a few things that we should discuss before we move on. And the first thing we should discuss is Exam 2. And I'm going to write Exam 2 and release it today. So, and it'll be due next Thursday. Okay. So that's Exam 2. I've already put a practice exam on the website, so there's a practice exam already up. We'll probably look at it today. Yep. Don't really have anything else to say about that right now, other than there's a practice exam and we'll look at it. What's the other things to say? Yeah, so the topic is going to cover generally self-balancing trees. As you can see from so like trees, self-balancing trees, heaps, so basically array-based heaps, skew heaps, leftist heaps, and binomial heaps. I was going to say Fibonacci heaps, but I never actually got to teach them this semester, so that makes me somewhat sad. The final is going to be a week long. Yeah, so I'll give you a week to do the final as well. I'll probably give it out. I'll probably give it out at the start of finals and just make it due on like maybe the day before the last day or the last day of finals. It'll be at least a week, something like that. And what else? Oh, and hash tables. Okay. So those are the three things that are going to be on this exam. So the final exam will be the same format. As usual. Yep. I don't like giving any induction. Well, I mean, would it really be computer science if you didn't have to do induction? So, I mean, I can't say that there won't be any induction. There'll probably be some kind of induction. Remember, induction is not a thing in itself, right? Induction is a tool. It's a hammer, right? So, like trees, like self-balancing trees, that's like a house. You know, a heap is like a McDonald's, and a hash table. Well, maybe the hash table is like McDonald's, and the heap is like, I don't know, some kind of factory, right? And you know, you can build all of those things with a hammer, and you can prove that you can make things with the hammer. But induction is really just the hammer. That's the way to think of it. So, so the answer is probably some kind of induction, probably some kinds of proofs, right? Because I mean, so the way to understand this class, right, is that the goal here is to. So here's actually my private goal. My private goal as a mathematician is to make this class about 85% coding and 15% math. Okay? And I don't know if it's going to be 75-25, 85-15, something like that. But then you ask, like, why does math have to be bigger than 0? And the answer to that is, the answer to that is that the math we do really helps us understand why all this coding stuff works at all, right? And so the thing is that if we didn't do any of the math, we wouldn't really understand. And the other actual secret goal, so you might say, like, okay, well, I don't really care why this stuff works, I just use it. Okay, so as a true empiricist, you would say, I don't care why. I only care that it works. And maybe you might say, well, that's not a true empiricist, that's a true engineer or whatever. And maybe that's an engineer mindset, not an empiricist mindset, but whatever. So the point is that that's one thing, but this is the other secret reason. The secret reason is that we're ramping all of you up to algorithms, which is, as it turns out, it's like 50, say maybe 25% pseudocode, 75% math. And so that's kind of, so this class is like the dual of 441 in a sense. In 441, they'll ask you to write algorithms, and you can write them in C++, but really what they want is like a pseudocoded algorithm, and at least for the most part. Now, some algorithms classes have had programming assignments, but generally you actually have no coding assignments in that class other than anything that's just on homework. So everything is like a math homework. And so like 25% is like pseudocode, and the rest of it is just math, right? Just understanding how algorithms work. And so that's really the whole point of all this. So, and I think today is a good day to say all this stuff because, you know, I know that I stress the coding in this class, and I do that intentionally, mainly because I am a mathematician, and if I didn't intentionally stress the coding as hard as I do, we could end up with like a 50-50 class where it's 50% coding, 50% math. And I think actually that would be, in a way, it'd be less helpful. I think it's better that you understand the coding of the algorithms and how to make the stuff. When you get to algorithms, you're going to be expected to understand, you know, more theoretically how they work. Okay, so yeah, so probably some kind of proofs. I don't know exactly which proofs I'm going to put on yet. I'll look through the things that I've given in the past and do something like that. So we'll talk about that kind of stuff. Final exam will be the same format. The study day, I think, is May 13th. I was looking up the schedule. I think May 13th is the study day. So I guess May 14th, therefore, the first day of final. And if that's the case, let me see. So if the 14th is the first day of the finals, then the 20th is the last day of the finals. Yes, 20th is the last day. And so what we're going to do is I'll probably release the final exam maybe the 12th or the 13th, and we'll have it due maybe on the 18th, like maybe the 12th to the 18th or something in that range. I could even release it on the 11th and have it due on the 17th on our actual final day. That way, something like that. Anyway, so that's kind of the current idea. The reason why we would want to do something like this is just because remember that at the end of this semester, there's like, I know it's not completely relevant to you as a student, but this is the reason why we have to do things in the ways that we're about to do them, is just because at the end of the semester we have end of semester plus 3 days to get all grades in. Okay? And so, as it turns out, that's not a lot of time. And if you remember, I'm also doing CMSC 201 and this course. So basically, it's going to be a lot of work, right? So that's why, you know, if you ask, like, can I have an extension? The answer, like, it might be good if I make the due date the 17th, because then I could say, okay, the extension is to the 20th or something like that, rather than putting it past the end of finals or something. But after the 20th, there really cannot be any submissions. And the reason for that is that I only have a few days to like compute everything and get it turned in, and it's a big scrum. It's a big mess. And so, you know, there's just a lot to do, and not much time to do it. And so that's the reason why I'm kind of trying to schedule this in like the perfect way to give all of you about a week to do the final, but also to give myself enough time to grade the final and then calculate your grades. So that's going to be the main compromise here, right? So we have to balance. It's definitely a balancing act, right? It's not something that there's a perfect answer one way or the other. But I think maybe this is a good thing, because if I release it on the yeah, I mean, the thing is that if I give an extension, hopefully what that will mean, but I mean, I think if you're gonna need an extension on the final, you're gonna have like documentation. You're gonna have to have a real good reason for that. Just because I'm gonna give you multiple days to work on it, And so, and as I say, you might say, well, you're being more strict than you were for exam 1 and exam 2 and all the homeworks and the projects and all that stuff. Yes, because it's not me, it's the fact that the university is about to, they will crunch me, right? There's a big time crunch coming in on me after the last final is submitted. So we just have to be kind of mindful of that and just make sure that whatever plan we have in place, you guys have enough time to do what you need to do, and I have enough time to do what I need to do, so that we can all actually get grades. So, okay, cool. So that's being open and honest about both sides of what's going on here. Okay. All right, the other thing to mention, and I know that I'm doing a lot of announcements, but I feel like this is a good time to do it since it's not, this lecture is kind of going to be freeform a little bit. So let's talk about Project 2. So I don't know if you've heard, cycling around, there was a discussion about Project 2 that happened amongst the professors, and excuse me, I'm about to sneeze. Okay, sneezing done. Okay, let me find the email because it has an equation in it. Okay, got the equation. So, performance on Project 2 was as expected. Yeah, thank you. I know, alright. So, Project 2 performance was terrible. But, on the other hand, you might say, but hey, Project 2 was mega hard. And basically, 2 projects Frankenstein monstered together. Right? And it was hard, and unfair, etc., etc. The true answer is, like, I hear you, and I care. I did try my best to warn all of you, and I think some of you took it, and some of you did really well in the project, and some of you were absolutely annihilated by it, and that is exactly what happened last semester, and we did by the way, we did warn the course chair that this would happen again. This was not unexpected. We were setting you guys up for failure, is basically what happened. The true average current is 65 for the whole course, and for our section, it was like 65. So you guys, now if you think, oh, we did terribly relative to everyone else, and maybe Eric really unprepared us, and this was like the worst project, and no, you guys did identically to the rest of the course. Everybody got hit. It was terrible. So that's that's the situation where we are. Adam came up with, or I should say Dr. Bartail, came up with a calculation, which all the other professors actually seem to want to adopt, and I'm just happy that he came out with it before I had to write anything up or do anything like that. So here is his calculation. So your new grade is going to be your raw score divided by 100 times to the 0.6th power plus a 5 offset. I don't know, did I type in the 4 isn't there? So then times 100 again, and then rounded to whatever. I mean, you can get rid of the round, right? So, yeah. I guess you can keep the round, right? Or maybe even floor or ceiling or whatever. Who cares? Into 5 is thing, right? So this is the equation that we're going to use to calculate your new project grades. So I will post those on, what am I going to post them on? Tell me where I'm going to post them. I'm going to post them on Blackboard. I'll post 2 grades on Blackboard. I'll post your original grade, and I'll post it as a doesn't count thing, and then I'll post your updated grade as the thing that'll actually mess with your numbers. So, so let me see here. Let me see exactly how this equation works. It's a bit of a Okay. So a 91 goes to a 99. Oh, very nice. Let's see what happens to the average. Oh, okay, actually. So that moves our class average, now that I've just done the calculation again. No. It's 0.6 to the power 0.6 plus the offset 5, not to the 5th power. Otherwise that would be very bad for you, right? Because if you took a number where your grade is now like grade divided by 100, which is between 0 and 1, right? If you took something between 0 and 1 and raised it to the 5th power, that's bad for you, right? Because that shrinks that number down. Like if your grade was like, if your grade was what, a 75, let's see what happens if your grade was a 75. I know this is totally irrelevant, but yeah, 0.75 to the 5th power would be 23%. So this would curve a 75 down to a 23. Anyway, no, point is that basically what this is doing, actually let's do it on some, so it curves a 90 up to a 99, it curves an 80 up to a 92, it curves a 70 up to an 86, it curves a 60 up to a 79, and it curves a 50 up to 71, and then maybe I'll do 40 and 30. So this is what it does, okay? Oops. So this is the way it curves. So a 90 becomes a 99, 80 becomes a 92, 70 becomes an 86, 60 becomes... So I would say that's actually a pretty good way to curve. I mean, yeah, I mean, that's not bad. That's not bad. It does everybody a service, right? So nobody, I mean, so the good news is, A, nobody's hurt, and everybody's helped. And, you know, it's kind of a, shall we call it a progressive system, where the people who need, like down here, up here you only get a 9-point curve because you're already getting an A, and it just moves you up closer to being 100. 80, you get like a 12-point curve, so that helps you more. This gives you a 16-point curve, 19-point curve, 21, 23, and 24. So it kind of increases the curve amount as the grade is lower, and that's good because it makes sure that nobody passes anybody else, so everybody's grade is in the same position relative to the class, but also everybody's grade goes up. All right. And it's not just a simple offset. Okay, so that's how this works, and I'm going to stick to his system because can scores go above 100? I think they could if you got like a 90. Let's say that you already had. So if you had 100, you get a. Yeah. So there are 2 people in the class who ended up with over 100 based on the curve. And there's another few people who ended up... So if you have a 92 or above, you either got 100 or above. Because of this +5 offset. So this is just a linear offset. And so the linear offset can easily push scores above 100. This can't actually push scores above 100 because this is taking a number between 0 and 1, raising it to a power, which is just another number between 0 and 1. And then you multiply it by 100, which is a number between 0 and 100, and then this adding 5 just gives you between 5 and 105, right? Okay, so that's it for the... So I wanted to mention this Project 2 curving because I think that it had been going around in other sections, and I didn't want you guys to think that, like, that I wasn't going to do anything. I was... So here were my 2 plans, which, I mean, since I've told you this plan, this is going to be the current plan. But the other plan, so the 2 plans were A, do this type of thing, you know, but Dr. Did it first, or B, don't curve anything, and just curve final overall grades, right? So I don't mean don't curve anything. What I meant was don't curve anything specific. So, and then just curve the overall final grades. So that's the those were the two plans. I usually just kind of do this one. Oops. I usually just do this one, the part B one, because let's say that you actually did do well on project 2, but you actually didn't do as well on project 3, or you didn't do as well in project 1, or you something, then actually this one helps people more on, I think this one kind of evens it out and helps people more on average. But I might do a little bit of this anyway, but it will be far less now that the project 2 issue is, I'll consider this quote-unquote solved, right? I think that Adam's curve solves the problem in a very intelligent way. No reason to challenge it, no reason to do anything differently. It'll be uniform and course-wide, and so that's what we're going to do. If, on the other hand, there's like a 1 or 2% curve in the actual final course grades, that's a different story. Okay. So, all right, so that's basically it for announcements. I've used 20 minutes on announcements, but again, I think it's probably valid because there's not a lot of time, there's not a lot of places to inform people about what's going on in the world. So, let's see here. Do I want to go over the practice or the previous exam too? That's a good question. I kind of want to go over it. Yeah, let's go over the questions. I'll just talk about them and talk about them. So this was an exam too that was given on paper. So so just keep that in mind that this exam, so an online exam is a fundamentally different type of object to a paper exam. So just be mindful of that. But the questions are actually, the good news is 341 questions can actually kind of make the gap. 201 questions, and I know this is not 201, but 201 questions have a much harder time of making the gap, so it's much different. Okay, so let's say I tell you to implement the Quicksort algorithm, right? Now, there's a bunch of different ways you can implement Quicksort. There's the in-place Quicksort, which you might have seen in some things, but I really don't care if you would just do something like, right? Just make some lists, and then you say for int x in the list. I don't know if you've seen this notation before. Okay. And then this is basically the same thing as saying int I equals 0, I is less than the list dot size, I plus plus, right? And then, anyway, so, okay, so what we're doing here is we'll say, if x is, say, less than the pivot, which will be the list 0, then, whoops, there we go. What is it? Something like that, I don't know why I'm doing this here. I should really be doing this in a compiler because I'm kind of dumb. And I know that there's not a concatenation for lists, but we'll have to, maybe what I actually have to do is something more like, in C++, unfortunately, since there's not a concatenation, we'd have to say like less list is equal to the quicksort of less list, equal list is equal to equal list, and and then greater, do the same thing on greater list. Right, so I'm just implementing quicksort, etc. Here, equal list. There we go. And then we return, and so then basically we need to, what we'll need to do is, and maybe I won't write all this out. I'll just say, put it all back into the, put it all back in. Something like that. You can even just overwrite everything in the original list rather than creating a new list. That's something different that I hadn't done before. Yeah, but this is basically quicksort. The only other thing that you need to do is to say that, right, if the, say like if the list dot, and remember, this is how you prevent is like say bigger than or let's say less than or equal to 1, we can just return the list. Right, something like that, to make sure that we don't do any infinite recursion. Okay, so this is basically the implementation of quicksort. So obviously I'll probably ask you to do merge sort, or maybe I'll ask you to do something else, I don't know. So I'll have to think about what I'm going to ask you to do. I probably won't ask you to just implement blah sort. I'll probably ask you some other questions about it, but it's good to think about implementation. So, okay. So here we go. Analyze the best, average, and worst case of quicksort, right? So let's do that. So what is the best case of quicksort? And so the answer is that in general, the best case occurs, and this is something that definitely, I don't know if I'll ask it in exactly these terms, but it's definitely extraordinarily important. It's something that you got to know like the back of your hand, right? You need to know the best, average, and worst case performance of quicksort. And so what I mean by this is that the best case of quicksort is when the the best case of quicksort occurs when every element, or when every division of the list, right, divides it into 2 equal halves, right? Or I guess maybe even 3 equal halves or whatever. It doesn't matter, as long as it's dividing it, the less list and the greater list are approximately the same size, right? Basically, I'm just saying less list is the same size as greater list, okay? So if that's the case, and of course we don't really care about equal list because we're not really doing anything with equal list anymore, so so the best case of quicksort, right, is going to be O of n log n, right? And so the reason is, right, and this is the reason that you should really understand now. It might not be 100% mathematically, rigorous enough to constitute a formal proof, but this is the reason that you should understand, and then this is the explanation that you need to be able to give, is that, when you divide a list in half, n times, or k times, I should say, right? Divide a list into halves, k times, you end up with n divided by 2 to the k sized lists, right? Now this is a perfectly mathematically true thing. There's nothing wrong with this. And then basically the argument here is that when n is approximately equal, right? Actually, what is the escape sequence for? Let's see, escape sequence for plus. Huh. Let's see if I can... No. No. Okay. I guess I could just use the math mode, but I really don't want to use the math mode just to say approximately 2 to the k, right? When it's approximately 2 to the k, that means that the number of steps is equal to k, and therefore, right, therefore, the number of divisions should be log n, right? Yes. Nice. Right, now that we have log n, then you ask, okay, now how much work does it take per division, right? Now every time we divide, right, we have to scan through all the elements again in all their different divisions. So basically, every time we divide, we scan all the elements once, and then we put them all back into a concatenated list. And so each one of those operations takes O of n time, right? Which is O of n total. Right, it's an O of n to scan the elements and put them in the lists, and then it's an O of n time to put them all back into a concatenated list. And then, what else do I say? Yeah, so then, as it turns out, log n, right, which is the number of splits that we had to do, times O of n is just equal to O of n. I'm sorry, O of n log n, right? And so, as it turns out, this is the best case analysis, right? This is the best case analysis that you gotta know, all right? So, you divide a list into halves, k times, you end up with n divided by 2 to the k times size lists. Now, of course, that might not be an integer, blah, blah, blah. Just pretend it's close enough to an integer, or, you know, it's either rounded up or rounded down. You don't really care that it's not an integer. What you're really saying is that we divide it until this gets down close to 1, and then when it's close to 1, that means that Quicksort is done, and that all the stuff has been split up into one-size lists, right? And then you just have to look at the function to know, right? This function, without the recursion, right, without these recursive steps, this for loop here is an O of n for loop, and this put it all back into the list is an O of n operation, right? That's the way to look at this. This is O of n, this is O of n. This part is the recursion part, which is happening log n times, right? And so that's why you look at it this way. Okay, so now let's look at the average case. All right. So the average case of Quicksort, okay? What is the average case of Quicksort? The average case of Quicksort is actually also going to be O of n log n, right? And you should ask, well, why is that the case? And the answer is, I'm not going to expect you, so I don't expect a rigorous proof. I mean, not that the proof above was particularly rigorous. I think it's something that like the vast majority of computer scientists would probably accept. It is definitely like a combinatorial kind of computer science-y looking proof. I mean, especially if you spruce up the language and turn these, you know, arrows into sentences and all that. If you make it more professional looking, this would definitely be a more acceptable proof. This one I think is a bit more difficult because there's a lot of different ways that I've attempted to show this kind of purely mathematically and do a lot of exacting calculations. They get very complicated very quickly, and it involves like the expected number or the expected size per splitting and that kind of thing, or the probability that you would split and the probability that you... So remember, I guess I'll say this before we get into the proof. Let's discuss what the problem with Quicksort is, and what is the worst case. So a sorted list right, is the worst case. And the reason why is because you pick the pivot is 1, and then 2, 3, 4, 5 goes into the greater list, and nothing else goes anywhere, right? And then you have 1 here, and then you'll have 2 is the pivot, and then 3, 4, 5 goes into the greater list, and then you'll have 1 and 2 here, and then 3 comes out, and 4, 5 are, in the greater list, and then you do it again and again and again, and so finally you'll get 4, 5 like this, and let's see. I think first you'll get something like this, where the 5 is the greater list, and then you'll end up with 1, 2, 3, 4, 5 all split up, and then you have to go back and merge them. So then 4 and 5 merge together, and then 3, 4, 5 merge together, and then 2, 3, 4, 5 merge together, and then 1, 2, 3, 4, 5 merge together. And so that in total will take this, and so this is the worst case analysis. So maybe I should actually say this is the worst case. And the worst case of quicksort takes on average about O of n squared time. And the reason why it takes O of n squared time is because of the Gauss sum, right? My favorite sum. It's the sum that makes everything work in computer science. That all the basic algorithms, all the basic trees and sorting and searching and all this stuff. If you do anything in mathematics, it's always the Gauss sum, which is just 1 plus 2 plus 3 plus 4 plus 5 plus ... plus n is equal to n times n plus 1 divided by 2. Right? That's it. That's what the Gauss sum is. It's just adding up a whole bunch of it's the sum of integers up to n. You can call I'm sure you can call it a lot of different things. I kind of call it the Gauss sum. You can call it like the Faulhaber formula of degree 1, or you can call it there's a lot of different things you can call it. But who cares what you call it? The point is, it's this thing, right? This thing is the thing that makes this O of n squared, right? Because every time you do this process, right, first you search through all 5 elements, then you search through 4 elements, then you search for 3 elements, then 2, then 1, then you remerge 1, 2, 3, 4, 5. So it's 5, 4, 3, 2, 1, 1, 2, 3, 4, 5. And when that happens, right, what you're going to see is that you actually have 2 Gauss sums added together in terms of like the number of steps that you're going to find. And so you're going to get O of n squared. Now, remember that the n over 2 disappears. The n times n, n times n plus 1 is really just n squared over 2 plus n over 2, right? And the n over 2 is a lower order term, right? Lower order. And so basically what that's going to do is that's going to, what should I say? That's why all the rest of this crap vanishes and you just have O of n squared. So yeah, so that's the worst case analysis. And I know I wanted to do the I wanted to do the average case analysis, which I will, let's call this, so worst case analysis. And I don't expect a rigorous proof here either, and this I think is good enough as a worst case analysis, right? Because you might say, well, that's not really proving anything because it's only bad on a list of size 5, and it's not taking that long, and it's going to happen in less than a few milliseconds, and blah blah blah. But you know what the point is, right? Like, yes, I know that this drawing only has a 5-element list, but then you just say, okay, take 5, off to infinity, right? So basically, what I mean by that is, take 5 out, replace with n, take n to infinity, and there you go, right? And so you're going to see that, or even, you don't even have to take it to infinity. First, you can just take it to big, right? Like 1,000,000 or 1,000,000,000 or something like that, and before you take it off to infinity. So, so that's kind of how to think about that problem. And so now let's talk about the average case of quicksort. And so the average case of quicksort, again, this is the most complicated case, okay? And the reason why is because you ask yourself, okay, what do I consider to be average, right? What is an average list? Is an average list a near sorted list? Is an average list literally any possible list? You know, what kind of sample space am I working on? What probabilities? So let me just say that if you did this, there's a lot of questions about exactly what this computation should mean, and it changes the computations a little bit, and it changes all the meanings, and it changes everything about everything. But in the end, we want to get O of n log n, and the question is why we want to get O of n log n, and why that should be the correct answer, right? So let me see if I can justify, maybe not quite call it a proof, but justify, right? So not really proof, but reasons, right? Here's the reasons why the average case of quicksort is n log n. And so think about it this way, right? Let's say that on average, you divide the list in half the time, and the other half of the time, you do the worst case thing, right? So let's say, I mean, this is not exactly how the average case analysis should go. There's a lot more mixing that happens where, what if you divide it 1/4, 3/4, or 2/4, blah, blah, blah. But let's be ultimately simple, and let's just say half the time you divide the list in half perfectly and you're happy, right? And the other half of the time you split off one element, right? And then you're unhappy because you're splitting off one element as the pivot into like the equal group, and everything else goes either into the greater category or the lesser category, right? And so it's a problem because you're thinking to yourself, man, like, I just did this splitting and it didn't really help me at all, right? It didn't make my problem any simpler, really. It just took one element out of 100,000 elements, right? It's still a I shouldn't use that word. I was going to use the word heap, but I don't actually mean that. I mean the philosophical heap problem, not the computer science heap problem. So, okay. So yeah, let's say that, and so if this is the case, that you divide, every time you divide it in half the time you're going to do the best case thing, and half the time you're going to do the worst case thing. And you can say, well, on average, that sounds like an average case, right? Sometimes we get the worst case, and you might say, well, maybe it's not exactly the worst case. Maybe instead of dividing off all the elements, it divides off 3, rather than, maybe it divides off 3 things, rather than, what should I say? 1. Or maybe it divides it into 4th and 3/4, or 7/8 and 1/8. But let me justify this. So basically, if this is what happens half of the time, then what we can basically assume, right, is that the number of steps is going to double, right? Because what we're doing is half the time we're dividing in half. So what we need is that, right, so 2 to the k over 2 is going to be equal to n. So the log of n is going to be equal to k over 2. So 2 log n is going to be equal to k this time. And now you know what's about to happen, right? And each step still takes O of n time, and 2 log n times the class of functions in O of n is actually just, and remember, constants get absorbed in that big constant c, so we're just going to have O of log n times n, or more popularly written as O of n log n, like that. And so that's exactly why the average case is what it is. So that's what I wanted to go over with Quicksort. So I think I spent a lot of time on Quicksort just now. Isn't that weird? Maybe this is exam review. I mean, I guess what this lecture is exam review. So that's fine. Oh, crap. I don't want to call it exam review because let's call it 341 exam 2 review. There we go. That's a name I haven't used. Okay. So let's look at some other problems on this exam. I might not be able to have time to do everything. So AVL trees, insert some stuff into an AVL tree. Let's see if we can do that real quick. All right, let's snip out the AVL tree and just do some insertions. This is just to help us remember, right? You're thinking to yourself, you're like, well, hey, you know, what's an AVL tree? You're like, I don't know. Who knows, right? Who knows what an AVL tree is anymore? So, okay, so here, I think actually I'll probably want to make the circle maybe a little bit. You know what actually I should do is I should just draw the circle like that. I think that's about the same size. Is that about the same size? You know what? Close enough for government work, because as it turns out, we are at a state university. So yeah, so the point here is that if we insert 10 into a binary search tree, you know, most of you are going to say, okay, stick it in here. And now let's just recall, right? And of course, by recall, I use recall in the sense of a mathematician's use of recall, which always meant recall or relearn, or maybe have to look up for the first time, or some combination of those things, right? So what's the property of being AVL, right? The AVL property is that the absolute value of the height of the left minus the height of the right is less than or equal to 1, right? That's the definition of the AVL property. So wherever you are, you look at the height of the left child and right child, and you ask, are they different by more than 1? And so here, this is height. Let's say that this is height 0, so the two children are null leaves at -1. So, okay, cool. So this is height 0. So then this will be height 1, but remember, that doesn't matter. Its children are height 0 and -1. So 0 minus -1 is 1, so that's okay. Here the height is 1 and 0, so 1 minus 0 is 1, so that's okay. Right, and so now here, the heights are, remember a single node is going to be considered height 0. This one is height 2, so 0 minus 2 or 2 minus 0, it doesn't really matter since it's absolute value. Right, 2 minus 0, 0 minus 2, that's a problem, right? So now what we have to do is we have to look at it. So remember that this was inserted in a zigzag, right? So it went right, left. So we got to do the rotation of 15 up. I'm sorry. First we got to rotate what? We got to rotate 10 up to... Oh, no, I'm sorry. Yeah, we got to rotate 15 up here and then 15 up there. That's right. Sorry. I had to remember for a second. Look at me remembering. I just got lost as to where we were for a second. I was like, where am I in this tree? Okay, so let's do this, right? Let's draw this thing out. Here we are. Unfortunately, we have to kind of redraw everything since that's actually just a static image. There's no... the only movable position is the 10. So here's 17, 15, 16, 7, 5. And so remember what we're doing. We are going to rotate 15 up. So let's try to do that. So 15 gets rotated up. And there we go. And then we're going to rotate 15 up again. So 15 gets rotated up a second time. So 10 comes down and is now the right child. 15 is now the root. And that's it. All right, that's it. Once we do this, we're good. Right? So that's what happens, right? So this was a zigzag rotation. And remember that the node that it was triggered on was not the node that actually got inserted, right? The node that it was triggered on was either you could say it was triggered on the root, or you can say it was triggered on 15, right? I don't care whether you say it was triggered on the bottom or the top of the rotation, but like, because we never really discussed like trigger on. I'm just inventing that term to describe what's happening here. But the point is that if it's triggered on 15, then that gets rotated up twice. So maybe that's the right way to talk about it. Okay, so now we want to do something like inserting 12. So 12 is going to go in to the BST here, right? And then you will say, is this AVL? And the answer is this is AVL and this is AVL, right? Because this is -1 and 0. This is 1 and 0. This is -1 and 0. So this is height 1. This is height 2. So 2 and 1 have a difference of 1, so you're good. And you never check 15 because 15 has the height that it has, right? It doesn't have... The reason why you never check the height of 15 as the root is because it has, you know, what should I say? It has... has no siblings, right? The root is its own thing. Okay, so now we are going to insert 20. So 20 gets inserted here. Yep. So 20 should get inserted here. And basically it's going to fail at 16, right? It's going to fail at 16 and then it's going to do a zigzag. So it's going to pull 20 up. So all right, so the first step, what it's going to do is it's going to pull 20 up here. So it's going to do this, push 17 down, pull 20 up. And I'm not going to redraw the lines because we're about to delete the lines again. And we're going to push 20 up, push 16 down. And so what's going to end up happening is, I know it's kind of smushing it in here, but that's what's going to happen. 20 will come up and become this node here. And this will be a really tiny little subtree. And this is a really wide subtree. But remember, that is just an optical illusion, right? It's a trick of the eyes because all pointers have the same length. They're all 4 or 8 bytes. So I guess they're not all the same length, but the point is made. So anyway, that's basically what I expect if I ask you to do something like that. I want you to rotate it. I want you to draw multiple pictures. I want you to describe how the rotations are happening. And I want you to kind of, you know, I mean, I've been using verbal words, but you can also just type in, you know, 20 is inserted here. Now we check heights, right? And then you say imbalance detected at 16, do zigzag or zag-zig or whatever. Right, zigzag double rotation. And then you say that fixes the height problems. And that's good, right? Like, I'm trying to encourage in life, as in many things, I'm trying to encourage a use of kind of maybe pictures and a use of explanatory notes and all that stuff, because I think that's the most helpful way to describe these kinds of structures. All right, so let's go back to the exam and see what else we have. There was some confusion on the exam last time about what predecessor versus successor deletion is. And so remember that deletion can either take the predecessor or the successor. And that depends on the way that the tree is built. And so I'm telling you here to use the predecessor delete. And remember what the predecessor is. It's the largest node in the left subtree, right? The successor, which is the standard delete, right? Traditionally, you'll delete from the successor. And I think, you know, one of the reasons that you do that in general is because if you put, so predecessor versus successor delete, it's not completely random. What I will say, and I'm not sure if I've said this before, it actually has to do with the stupid edge case of where you would stick another 21, right? If you would stick a 21 to the left, you would use predecessor delete. If you would stick a 21 to the right, then you would use successor delete. And it just depends on the direction that the equal sign goes. Because the point is that if you pick the largest node on the left side, if you pick the largest node on the left side, and say it's equal to some other nodes on the left side, right, and you pull it up, then that had to be allowed, right? So if it wasn't, it has to be, it can't just be the, what should I say about that? It just can't be the, well, I guess in that case, maybe it's a little bit less specific, but I don't know. I think one of the general ways is that if the equal elements go to the right, then you generally use successor delete, and if the equal elements go to the left, then you use predecessor delete. I don't think it's 100% necessary, but I think that it's definitely kind of implied. So anyway, if you delete 46 from the tree and you use predecessor delete, then actually what you do is you just move 42 up here and delete this node, and then what you're going to notice is that nothing changes because this is actually AVL already. So when you go through this problem, the moral of the story of this problem is that nothing changes in the tree structure. You just delete 46 and you put 42 in its spot. That's all you do. So as you see here, I had a white-black tree rather than a red-black tree. And again, the reason for that was purely because we have a black and white copying machine, and also because sometimes the danger is if I actually made them red, it might just be gray when they print it out, and if it was grayscaled, then it might be hard to read the numbers. So it's a white-black tree now rather than a red-black tree. So anyway, the point is that you have to insert 14 and 150 into this red-black tree. So this is how you do it, right? So you say, I'm going to insert 14. 14 goes in down here, and 14 gets colored red-white, right? So it gets colored white. And you know that, here's the thing, you know that basically you have to ask a bunch, remember the questions that you have to ask. You have to ask, is the uncle red or black? And so if 14 gets inserted here, then the point is that here's its parent, here's its grandparent, here's its uncle. Now you might say it doesn't have an uncle, and I say, aha. But remember one of the red-black rules. The red-black rules say that what? That null nodes are black. So it's a black uncle, and so it's so it's a black uncle. So basically what we have to do is rotate and recolor. And so the right answer, what's going to end up happening is, since this is a straight line case, it's a black uncle, but it's a straight line case, you're going to just do one rotation. You're going to rotate 28 up, 63 down, 14 in this position. So let me actually redraw this tree. Maybe I will do this. Let's snip it. So here we go. Now we'll draw in a 14 here. And I'm not sure I'm going to redraw the whole tree because I don't want to waste too much time. But what I will do is I will kind of maybe, what we'll do here is, so this is what ends up happening, and then this is a red node, this is a red node. And so remember, this is the one way we can detect problems, in a, the one way we can detect problems in a red-black tree is to, I shouldn't say the one, the one way. The only way, right, is to know that there's a red child of a red parent. So that's the only way you can detect a violation. Now, the height violations and all that, they're undetectable because remember, you don't actually keep a height variable. You only keep a color. So here's what I'm going to do. Here's the cheap solution that I have. I'm going to do this. I'm going to do this. And then I am going to fill it in with white. So under that is all the stuff that we have. And now what I'm going to do here is There we go. Let's fix it now. So here, so 28 is going to come up. Right, so 28 is going to come up. Why is this so small? Maybe I made this way too big. Let's actually shrink this thing down a little bit. There we go. Now the font looks a little bit better, a little more right. Okay, so here's 28. Yeah, so actually let's merge these two things together. So now they're the same thing. All right, so let's put 28 here. Let's put this here, and let's put this here. And by this, I mean the thing that we're going to change to 14. And by the other one, I mean the thing that we are going to change to 63. And then what are you going to do? So what you're going to do is, then you're going to have to recolor, right? So this one's going to have to be the black node. I'll color it in gray like this so that you can see the, well, actually, maybe I'll just do this. Change this to white, change that to black, and then these can both stay as red. So this is how this will work, right? We flip the colors here because that's how you, after you do the rotation, remember, if you have the black uncle, you do the rotation, and then you have to recolor to make sure it works. So this is the recoloring that you would do. All right, cool. So now let's do this again. Only this time we're going to insert, I guess, 150, right? So where does 150 go? So as it turns out, 150 is just going to go in right here. And then we're going to do the same thing that we did before, right? Except this is going to be a zigzag rotation. So what we're going to do is rotate this guy up, and then 144 is going to come down, and then we're going to rotate 150 up. And so in the end, what we're going to see, and I guess we should actually make another little one of these, maybe. Cover this stuff up. So, yeah, let's cover that up. Let's get rid of the border. Let's make it white. Okay. This is all very bad way to do this, but I'm just trying to do it quick. So 150 is going to be the root here. We're going to have 162 down here, and we're going to have 144 down here. And so the answer here is that what are we going to do? So we'll have 162 here, and that's how it works. That's it, right? And so then you say, but wait, I have to recolor, right? So, all right, so let's recolor. I guess we can actually just recolor both of these black, right? Maybe these, the numbers can be. Well, they're done, right? The numbers should be white, but I can't find them now because they're okay. So that's basically what I want you to do in terms of this, okay? And yeah, so the reason that I think it's good to practice. So so the question for you should be, how should I do this? There's two ways to do this, and I would say, basically practice with the model on the website. Okay, so what I mean by the model on the website is, what do I mean? Red-black tree visualization. I mean this thing, right? So go there and just insert nodes, play with nodes until eventually you figure out that, until you figure things out. Okay, so, all right. Prove or argue compellingly that an AVL tree can be recolored into a red-black tree. So, the reason that this is true, and it's only true in one direction, right? So it's true that an AVL tree, I won't say an AVL tree is a red-black tree, but there's like a function that you can assign to an AVL tree that will make it into a red-black tree, and with no restructuring, right? No restructuring. Basically, that function, we could just call it RB color, right? It just takes an AVL tree and it colors it in a certain way, and it will make it into a red-black tree. Okay, so that's the point. There is actually, and then the opposite, or the converse, right? Converse is not true. There is no function which can like heightify, right? Because what does red-black have? There's no like heightify function that takes a red-black tree and turns it into an AVL tree. Okay, and so the reason that this is the case is because if you think about it, what does red-black do as opposed to AVL? And the answer is that red-black, the problem that red-black has, and the reason why you can't go backwards, is that I can do something like this, right? So all of this is on the left, and so this will be our red-black tree, and then here we have this on the, let's do this on the left, and then we'll say that this, okay. There we go. And so now let's color all the nodes so that they're proper colors. So these are all going to be black because the root is black, and then these 5 nodes are going to be red. And so the problem with this shape, right? What is the problem here? And so the idea here is that the problem is that if you look at the heights, right? And I'm not allowing you to restructure. The only thing I'm allowing you to do is attach heights, and the heights are pre-computed basically, right? Like there's no way that we can change the actual heights in this tree. So the height of these nodes are say 1. So these heights are 1, 2, 3, right? So the difference here is 3 minus 1, which is 2, right? Which is bigger than 1, so not AVL, right? So basically the moral of the story here is that there's no heightify function that like strips this red-black tree of color and adds heights into the nodes, right? There's no way to do that particular operation and yet be guaranteed that the thing will actually be an AVL tree, right? Now, it's possible you could say, well, we could do some rotations and fix it, but the answer is that's not the question, right? The question is, can you take this exact structure, which is definitely a red-black tree, and make it into an AVL tree, right? And the answer to that is no, you can't. And you can't, and it's not just because like AVL, the real reason for this is that AVL tree rules are just stricter, right? That absolute value being less than or equal to 1, as it turns out, is just a much stricter rule than the red nodes can't have red children, right? So that's a weaker rule, okay? And so AVL trees are a stronger rule. Red-black trees have a weaker rule. And I mean, they both maintain balance for the purpose of like logarithmic stuff, logarithmic search, insert, delete. Yeah. Okay, so I think that's all I really want to say about AVL and red-black. I never actually did prove or argue compellingly that an AVL tree can be recolored, so I just told you that it could be. The reason is because if the heights match, you can basically just color almost everything black, right? The secret reason is that you can color almost everything black, except maybe a few nodes which need to be red. And so I want you to, if you want to think about this, like, you can draw out some examples of where this is going to happen. So it's not the only red-black coloring. So I'm not saying that the only red-black coloring, like all AVL trees, must just be these like completely or mostly black, red-black structures. But the tricky way to do it is basically to color almost everything black, and then just to be like, well, if the heights are different by more than one, then you just make one of them a red node, and then you just keep going down, and then it should be a balanced black height. Everything should be fine, and there you go. But yeah, you'll have to think about that. It's a complicated problem, but you have to think about it. Okay. And so what else for the rest of these questions? So I was going over hash tables previously. We've just done heap stuff. And then, of course, the question is, what about the stuff about depth first search, breadth first search, all that stuff? Well, I was thinking about talking about graphs the next 3 classes. So that stuff will be on the final. It's not on exam 2. Okay, so we will talk about DFS, BFS, A star, and Dijkstra. But just because we'll discuss those things does not mean that they're going to be on this exam. I think that semester the timing was just different, so we had covered slightly more by that point in the semester, and all the standard excuses for why things worked or didn't work or whatever. So that's the point. Okay, that is the point. All right. I think that's all I really have to say about this midterm. So this thing that I gave as a practice midterm, I'm 80 to 90% sure. I think this was the exam that I gave, or maybe I gave something shorter than this. Maybe I just like turned it down a bit. So, but anyway, the point is that you'll probably see, as I say, you're going to see maybe sort questions on quicksort, merge sort. You'll see AVL, red, black, heap questions, hash table questions. So that's what the exam is going to be. And I haven't gone over the hash table stuff mainly because I've been going over that for 2 lectures just now, so watch those lectures instead. Actually, really just watch the first one. The second one is a repeat of the first one, and after I had my COVID vaccine, I was kind of delirious for about 2 days, and I'm not sure that my 201 lecture on that Monday made any sense, and I'm pretty sure that the lecture this Tuesday didn't make all that much sense. And that's unfortunate, but that's the way it was. I don't think I made... Wait a second, this is a trinary tree. Goodbye, node. Something about that was bothering me. Right? Like that was not perfect, right? Like there were 2 nodes on this side, so this node had 1 left child and 2 right children. Anyway, fix that. Okay. Now I feel better. Something looked wrong, but I couldn't understand because I hadn't drawn in the lines. Okay. Maybe the last thing I'll do in maybe 1 minute is to just discuss this stuff, because I don't think I've talked about this a lot during the lectures, the actual runtime of the heap algorithms. And I think when I was talking about this, this was part B of an array heap thing. So I should have. So this is array heap, right? This is part B. I just said heap here, but so okay. So basically, what is the best case for an insertion into an array heap? And the answer is that you insert it at the end of the array, and then it doesn't require any swaps. So that's O of 1, right? You insert and no swaps. Okay, so that's a pretty good best case. Maybe I should make this thing bigger so that I can actually fit this stuff. Ugh, terrible, terrible. There we go. Insert no swaps, right? And this is the array heap. And by swaps, I mean no percolation. Delete is, I guess the thing is, like, maybe it can be about O of 1 if you put it in the, and you only have to maybe swap it once or twice. You probably won't have to swap it 0 times, but you may only have to, you know, may swap 0 or 1 times. Now, here's the thing about merge. Remember, for an array heap, unlike the Fibonacci heap, which I haven't talked about, the binomial heap, the skew heap, and the leftist heap, unlike all of those heaps, merge in this case requires a complete reconstruction. Okay, so it's going to take you O of n log n time. Okay, so merge is an O of n log n time thing. Okay, so, and that's in the best case. So the best case is O of n log n. The expected case is O of n log n. The worst case is O of n log n. The expected case of insert is probably O of log n. And what is the worst case? So unlike the leftist heap and the skew heap, which can actually kind of form themselves into lines in the worst case and get an O of n once or twice, the worst case in an array heap is always log n. And it's the same thing for delete and here. So this is basically the table that you should know. You can also check this out on, I think, Wikipedia. They have a lot of they have some information on this kind of stuff. Anyway, so I just wanted to discuss let's see here. Okay. Yeah. All right. So I think I'm good on that. So all right. I think that's all I really have for today. I just wanted to write this table down because I know that this table was kind of a disaster when I gave it on that exam. So that was a very bad table that a lot of people said some pretty crazy stuff on it. I mean, some stuff that, like, I really did not believe that would be said. So, you know, if you learned anything about most of these heap operations, right, they mostly run in log n time, unless they're in the worst case. But even in the worst case, the array heap, right, not the leftist heap, not the skew heap, the array-based heap, right, always inserts and makes a complete tree, right? So it's always logarithmic, even in the worst case. So the best case is you don't have to do any percolation, it's O of 1. The worst case is that you do a log n. The expected case is that you do probably some log n. Maybe you have to do half of the percolations. It comes up, you know, a few times, but not the whole, you know. So that's generally how to understand this table. Okay. All right, I think that is it for today, as I've said like probably 3 times at this point, so I'm going to let everybody go. Yeah, also I'll write and release the exam sometime tonight, and that'll be that. All right, so this, I guess today was an exam review, so that's what I'll name this lecture, so that other people know what it's actually going to be, rather than what I thought it was going to be. I honestly didn't really know, I guess, so we'll just call this Exam 2 Review and Announcements. Okay. Not a terribly exciting lecture, but it's necessary because it's the nature of the universe. So, all right. Yeah, I'll post the lecture notes. You don't have to ask every time, but I will do it. Okay. All right. Let's end the lecture. I'm just actually trying to find OBS. Here we are. We're out.